Tonight, as you settle into this quiet moment of contemplation, I invite you to imagine yourself lying on a soft blanket beneath the vast expanse of a clear night sky. Above you stretches an infinite canvas of velvet darkness, punctuated by countless points of light that seem to dance and shimmer with a gentle, rhythmic pulse. Each star appears to breathe with its own soft luminescence, flickering between bright and dim in a cosmic ballet that has captivated human hearts and minds for countless generations. As you gaze upward into this celestial dome, allow yourself to become aware of something truly remarkable. Those distant suns, burning with nuclear fire across unimaginable distances, are not actually twinkling at all. The steady, constant light they emit travels through the vacuum of space for years, decades, or even centuries before reaching the edge of our planet's atmosphere. Yet somewhere in that final moment of their journey, in the last few dozen miles before reaching your eyes, something magical happens that transforms their steady radiance into the gentle, dancing shimmer we call twinkling. This transformation is one of nature's most beautiful illusions. A cosmic sleight of hand performed by our own atmosphere that has inspired poets, guided sailors, and sparked the imaginations of dreamers throughout human history. The question of why stars twinkle touches something deep in our relationship with the night sky, connecting us to both the scientific wonder of atmospheric physics and the timeless human experience of lying beneath the stars and marveling at their mysterious dance. Consider for a moment the extraordinary journey that starlight takes to reach you. A photon of light, born in the fusion furnace of a distant star, begins its voyage across the cosmos, traveling at the ultimate speed limit of the universe, 186,000 miles per second. For years or centuries, this tiny particle of light races through the near-perfect vacuum of interstellar space, unchanged and unwavering in its path. It passes by planets and asteroids, through clouds of cosmic dust, around the gravitational wells of massive objects, maintaining its straight trajectory with unwavering determination. Then, in the final moments of its epic journey, this photon encounters something it has never experienced before: the layered, turbulent atmosphere of Earth. Suddenly, after eons of traveling in a perfectly straight line, the light finds itself bending and weaving through pockets of air with different temperatures and densities, like a river suddenly entering a series of rapids after flowing calmly across a vast plain. The starlight begins to dance and fluctuate in ways that create the gentle twinkling we observe from the ground. This phenomenon, which scientists call scintillation, is the result of our atmosphere acting like a constantly shifting lens. The air around our planet is not uniform. It exists in layers and pockets of varying temperature, humidity, and density. As these air masses move and swirl, driven by winds, thermal currents, and pressure changes, they create subtle variations in the atmosphere's ability to bend light. When starlight passes through these invisible currents and eddies, it gets refracted, bent slightly this way and that, causing the star's apparent position and brightness to fluctuate rapidly. Picture the atmosphere as an ocean of air, with currents and waves invisible to our eyes, but very real in their effects on light. Just as looking up at the surface of the world from underwater shows you a shimmering, dancing view of the sky above, looking up at the stars from the bottom of our atmospheric ocean shows us their light filtered through these same kinds of optical distortions. The stars themselves remain perfectly steady in their nuclear burning, but their light reaches us through this sea of moving air, carrying with it the signature of that final atmospheric journey. The beauty of stellar twinkling lies partly in its unpredictability. Unlike the mechanical regularity of a lighthouse beacon or the steady glow of an electric bulb, each star's twinkle is unique, created by the specific atmospheric conditions that exist along the path its light takes to your eyes. The pattern changes from moment to moment as air currents shift, temperatures fluctuate, and pressure systems move across the sky. No two stars twinkle in exactly the same way, and the same star will twinkle differently from one minute to the next, creating a display of natural randomness that seems almost alive. This atmospheric dance affects different stars in different ways, depending on their position in the sky. Stars near the horizon, sitting low on the celestial sphere, must send their light through much more atmosphere to reach your eyes than stars directly overhead. Imagine looking at a coin lying at the bottom of a shallow puddle versus one at the bottom of a deep swimming pool. The deeper the water, the more distorted the image becomes. Similarly, the more atmosphere starlight must traverse, the more opportunities it has to be bent and scattered, making stars near the horizon twinkle more dramatically than those high overhead. As you rest in this understanding, breathing slowly and naturally, consider how this simple optical phenomenon connects you to the vast cosmos beyond our planet. Every twinkle you see is evidence of our atmosphere's presence, a reminder that we live at the bottom of an ocean of air that protects us from the harsh vacuum of space while simultaneously creating this beautiful visual effect. The twinkling stars are not just distant suns, they are messengers carrying information about the invisible currents of air that surround our world. The colors in a star's twinkle tell their own story. Sometimes you might notice that a twinkling star seems to flash briefly red, then blue, then white. This happens because our atmosphere affects different colors of light slightly differently, bending blue light a bit more than red light in a phenomenon called atmospheric dispersion. As the air currents shift and change, they can briefly separate the star's white light into its component colors, creating momentary flashes of red and blue that add to the overall twinkling effect. Tonight, as you prepare to drift into sleep beneath this ancient canopy of dancing lights, remember that each twinkle is a small miracle, the result of light that began its journey in the nuclear heart of a distant star, traveled across the vast emptiness of space for years or centuries, and then performed one final dance through our planet's atmosphere before reaching your eyes. In that twinkle, the cosmic and the terrestrial meet, creating a display of natural beauty that has inspired wonder in human hearts since our species first looked up at the night sky and marveled at the gentle, rhythmic breathing of the stars. The ocean of air above. As you continue to rest beneath the starlit sky, breathing gently, in rhythm with the night around you, let us explore more deeply the invisible ocean that surrounds our planet. The atmosphere that transforms steady starlight into the gentle dance of twinkling we observe from Earth's surface. This ocean of air, stretching from the ground beneath you to the edge of space itself, is far more dynamic and complex than it might first appear. Picture the atmosphere not as a static shell surrounding our planet, but as a living, breathing system in constant motion. Even on the stillest night, when not a leaf stirs and the air around you feels perfectly calm, the atmosphere above is alive with currents, eddies, and streams of moving air. These invisible rivers of atmosphere flow at different altitudes, carrying with them variations in temperature, pressure, and humidity that create subtle but significant changes in the way light travels through the air. The scientific name for stellar twinkling, scintillation, comes from the Latin word scintillare, meaning to sparkle or to emit sparks. This poetic etymology hints at the fundamental nature of what we're observing. Each twinkle is like a tiny spark created when starlight encounters the turbulent boundary layers within our atmosphere. These boundaries exist wherever air masses of different temperatures or densities meet, creating zones of optical turbulence that act like invisible lenses, constantly shifting and changing the path of light passing through them. To understand how this atmospheric lens system works, imagine holding a piece of old, wavy glass up to a distant candle flame. As you move the glass or change your viewing angle, the flame appears to dance and shift, sometimes brightening, sometimes dimming, as the uneven glass refracts the light in different directions. Our atmosphere works similarly, but instead of solid glass, we have layers and pockets of air with different optical properties, all in constant motion due to winds, thermal currents, and pressure variations. The physics underlying this phenomenon involves the concept of refractive index, a measure of how much a material can bend light as it passes through. Different materials have different refractive indices. Water bends light more than air, glass more than water, and diamond more than glass. But what many people don't realize is that even air has a refractive index that varies depending on its temperature, pressure, and humidity. Warm air has a slightly different refractive index than cool air, and these small differences are enough to bend starlight as it passes through. When astronomers study scintillation, they often talk about something called the seeing disk, the apparent size of a star's image as it appears through a telescope due to atmospheric turbulence. On a night with poor seeing, stars appear as large, fuzzy blobs that dance and shimmer wildly. On a night with excellent seeing, stars appear as tiny, steady points of light. This variation in seeing conditions is caused by the same atmospheric effects that create twinkling for the naked eye, just magnified and made more apparent through telescopic observation. The atmosphere's effect on starlight is strongest in the first few miles above Earth's surface, where temperature and pressure variations are most dramatic. This region, called the troposphere, is where most of our weather occurs, and it's also where most stellar scintillation is generated. Above the troposphere lies the stratosphere, where the air is thinner and more stable, contributing less to the twinkling effect. This is why astronomical observatories are often built on high mountains, not just to get above some of the atmosphere, but to get above the most turbulent part of the atmosphere, where twinkling is strongest. The speed of atmospheric changes plays a crucial role in the character of stellar twinkling. The air currents and thermal cells that cause scintillation typically move and evolve on timescales of milliseconds to seconds. This is why stellar twinkling has its characteristic rapid, flickering quality rather than slow, gradual changes. The atmosphere is essentially creating a rapidly changing pattern of lenses and prisms that alter the starlight's path many times per second. Different atmospheric conditions create different types of twinkling. On humid nights, when the air is filled with moisture, the twinkling tends to be more subdued but more colorful, as water vapor in the air creates additional dispersion effects that separate starlight into its component colors. On dry, clear nights, especially when high-pressure systems create stable atmospheric conditions, the twinkling may be less dramatic but more rapid, with stars seeming to flicker quickly rather than slowly pulsing. Wind patterns at different altitudes also influence the twinkling we observe. Jet streams, those rivers of fast-moving air that flow at high altitudes, can create zones of enhanced turbulence that make stars twinkle more dramatically when their light passes through these regions. Weather fronts, where different air masses meet and create boundary layers, are particularly effective at generating the atmospheric turbulence that causes scintillation. The remarkable thing about atmospheric twinkling is how it varies across the sky in real time. If you watch carefully on a clear night, you might notice that some stars twinkle more than others, and that the same star might twinkle differently as the night progresses. This happens because the atmosphere above you is constantly changing, with different regions experiencing different levels of turbulence at any given moment. Weather systems moving through the area, temperature changes as the night cools, and even the passage of aircraft at high altitude can all influence the local atmospheric conditions that affect stellar scintillation. Modern meteorologists and atmospheric scientists have developed sophisticated tools to study these atmospheric effects. Doppler radar can track the movement of air masses. Weather balloons carry instruments up through the atmosphere to measure temperature and humidity profiles. And satellite imagery reveals the large-scale patterns of atmospheric motion. All of these tools help us understand the complex dance of air currents that creates the twinkling we observe in the night sky. For astronomers, atmospheric scintillation represents both a challenge and an opportunity. The twinkling that makes stars beautiful to casual observers makes them difficult to study in detail through telescopes. This has led to the development of adaptive optics systems, sophisticated technologies that use deformable mirrors and rapid feedback systems to compensate for atmospheric turbulence in real time, effectively removing the twinkling and allowing telescopes to see stars with unprecedented clarity. Yet there's something deeply satisfying about understanding that this cosmic light show is created by our own planet's breath, the constant circulation of air that brings us weather, distributes heat around the globe, and maintains the delicate balance of gases that makes life possible. The same atmospheric processes that create clouds and rain, that carry the scent of flowers on a summer breeze and the sound of thunder across the landscape, are also responsible for the gentle twinkling that makes the night sky so enchanting. As you rest here, breathing the same air that dances with starlight above you, consider how this invisible ocean connects you to the cosmos. Every breath you take is part of the vast atmospheric system that transforms the steady light of distant suns into the twinkling tapestry that has inspired human wonder throughout history. The atmosphere that sustains your life is the same atmosphere that creates the beautiful illusion of dancing stars, connecting the biological necessity of breathing with the aesthetic joy of stargazing in a seamless, elegant whole. The steady companions. As you continue your gentle observation of the night sky, you might notice something curious among the twinkling stars. A few bright objects that shine with remarkably steady light, immune to the atmospheric dance that affects their stellar neighbors. These are the planets, our cosmic companions, in their eternal journey around the sun. And their steady glow reveals something profound about the nature of light, distance, and the way our atmosphere interacts with objects of different apparent sizes. To understand why planets don't twinkle like stars, we must first appreciate the fundamental difference between how these celestial objects appear to our eyes and telescopes. Stars, despite being enormous, often much larger than our own sun, are so incredibly distant that they appear as perfect points of light, even through the most powerful telescopes. The nearest star beyond our sun, Proxima Centauri, is more than 4 light-years away, a distance so vast that even an object the size of our sun appears as nothing more than a dimensionless point from Earth. Planets, however, tell a different story. Though they produce no light of their own and shine only by reflecting sunlight from their surfaces, they are much closer to us than the stars. Venus, Mars, Jupiter, and Saturn, the planets most commonly visible to the naked eye, are all within our solar system, mere light minutes or light hours away, rather than light years. This relatively close proximity means that, even though planets are much smaller than stars, they appear to have measurable size when viewed from Earth. Through a telescope, planets reveal themselves as tiny disks rather than points of light. This difference in apparent size, what astronomers call angular size, is the key to understanding why planets maintain their steady glow while stars dance and flicker. Imagine looking at a distant streetlight through the heat shimmer rising from hot pavement on a summer day. The light appears to dance and waver because the rising warm air creates moving lenses that bend the light in different directions. Now imagine looking at a large illuminated billboard through the same heat shimmer. While individual points on the billboard might still appear to waver, the overall brightness of the sign remains relatively constant because the shimmering effects on different parts of the sign average out. This is essentially what happens with planets in our atmosphere. While the atmospheric turbulence that causes stellar scintillation affects planetary light just as much, planets have enough apparent size that the twinkling effects across their visible disk tend to cancel each other out. When one edge of the planet's disk might be brightened by atmospheric refraction, another edge might be dimmed, and these variations average out to produce a steady overall brightness that our eyes perceive as non-twinkling light. The mathematical principle behind this averaging effect is both elegant and intuitive. The amount of twinkling an object exhibits is inversely related to its angular size. The larger an object appears in the sky, the less it will twinkle. Stars, being essentially point sources with zero angular size, experience maximum twinkling. Planets, with their small but measurable angular sizes, experience reduced twinkling that becomes less noticeable as their apparent size increases. Jupiter, the largest planet in our solar system, appears largest in Earth's sky and therefore shows the least twinkling. Venus, despite being smaller than Jupiter, often appears even steadier because it comes closer to Earth in its orbit, giving it a larger apparent size during its brightest phases. Mars shows more variation because its distance from Earth changes dramatically as both planets orbit the Sun. When Mars is close, it appears larger and steadier. When it's farther away, it may show slight twinkling. This planetary steadiness has been recognized and appreciated by observers throughout human history. Ancient astronomers noticed that certain bright objects in the sky didn't participate in the stellar twinkling dance, and they gave these objects special names and significance. The word planet itself comes from the Greek word planetes, meaning wanderer, referring not only to their motion against the stellar background, but also to their different behavior regarding scintillation. The steady light of planets made them particularly valuable for navigation and timekeeping in ancient civilizations, while twinkling stars could sometimes be difficult to observe precisely due to their scintillation. The steady planets provided reliable reference points for navigation, calendar making, and astronomical observation. Sailors crossing dark oceans could depend on Venus or Jupiter to maintain consistent brightness throughout the night, unaffected by the atmospheric tremors that made stellar observations more challenging. Modern astronomical instruments can measure the subtle differences in scintillation between different celestial objects with remarkable precision. Professional astronomers use devices called scintillometers to study atmospheric turbulence by analyzing the twinkling patterns of stars. These instruments can detect variations in stellar brightness that occur many times per second, revealing details about atmospheric conditions that would be invisible to casual observation. Interestingly, the distinction between twinkling and non-twinkling objects can sometimes help amateur astronomers identify what they're looking at in the night sky. A bright, steady object is likely to be a planet, while a bright, twinkling object is almost certainly a star. This simple observational technique has been used by stargazers for centuries to distinguish between different types of celestial objects without the need for telescopes or star charts. The physics of planetary non-twinkling also explains why very bright satellites and the International Space Station don't twinkle as they pass overhead. These artificial objects are close enough to Earth that they have measurable angular size, and their reflected sunlight undergoes the same averaging effect that keeps planetary light steady. However, satellites moving through different atmospheric layers can sometimes show variations in brightness due to changing atmospheric conditions along their path. There are exceptions to the general rule that planets don't twinkle. When planets appear very close to the horizon, where their light must pass through the maximum amount of atmosphere, Even their relatively large angular size may not be enough to completely average out the atmospheric effects. During these times, careful observers might notice that even bright planets like Venus or Jupiter show slight scintillation, though it's typically much less dramatic than stellar twinkling. The color of planetary light also behaves differently than stellar light when affected by atmospheric scintillation. Stars often show rapid color changes as they twinkle, flashing red, blue, and white as different wavelengths of light are refracted by different amounts through atmospheric turbulence. Planets, due to their averaging effect, tend to maintain more consistent color, though they may still show subtle color variations when observed near the horizon. This steady planetary light has inspired different cultural and mythological associations than the twinkling stars. While stars were often seen as flickering flames, dancing spirits, or messages from the gods, planets were frequently associated with constancy, reliability, and divine permanence. Their unwavering light made them seem more substantial and enduring than the apparently fragile, flickering stars. As you rest beneath this celestial display, notice how the steady planets serve as anchors of calm light in the sea of twinkling stars. Their reliable glow connects us to our place in the solar system, reminding us that we are part of a family of worlds orbiting the same star. While the distant stellar fires dance through our atmosphere's invisible currents, these nearby worlds shine with reflected sunlight that has traveled only hours or minutes to reach our eyes, carrying with it the steady radiance of our own sun, transformed by alien landscapes into the gentle, unwavering beacons that have guided human navigation and imagination for millennia. Starlit stories beneath the same twinkling canopy that stretches above you tonight. Countless generations of human beings have gazed upward and wondered at the dancing lights in the darkness. Long before anyone understood atmospheric refraction or scintillation, our ancestors created rich tapestries of meaning around the gentle flickering of the stars, weaving stories that connected the cosmic dance above to the rhythms of life below. These ancient perspectives remind us that the twinkling of stars has always been more than just a physical phenomenon. It has been a source of wonder, guidance, and spiritual connection that transcends scientific understanding. In the earliest human cultures, the twinkling of stars was often interpreted as evidence that these celestial lights were alive. To eyes unacquainted with the concept of distant suns burning with nuclear fire, the gentle pulsing of starlight seemed like cosmic breathing, the slow heartbeat of divine beings scattered across the heavens. The ancient Egyptians saw in the twinkling stars the souls of the departed, flickering with the remnants of earthly life as they journeyed through the afterworld. The brightest stars, those whose twinkling was most prominent, were thought to be the most recently deceased, still pulsing with the memories of their mortal existence. Greek mythology painted the twinkling stars as the tears of the gods, each flicker representing a moment of divine emotion cascading down from Mount Olympus to the mortal world below. The Pleiades, that beautiful cluster of stars that seems to shimmer with particular intensity on clear nights, were said to be the 7 daughters of Atlas, transformed into stars but still weeping for their father's eternal punishment. Their collective twinkling was seen as a celestial display of sorrow and sisterly love that could move even the hardest human heart to compassion. Aboriginal Australian cultures, with their deep connection to the natural world and sophisticated astronomical knowledge, interpreted stellar twinkling through the lens of the dreamtime, that eternal realm where past, present and future coexist. The twinkling of stars was understood as the campfires of ancestral spirits flickering in the wind that blows between the worlds. Different patterns of twinkling carried different meanings. Rapid flickering might indicate ancestral urgency or warning, while slow, gentle pulsing suggested peaceful approval from the spirit world. Ancient Chinese astronomers, who developed some of the most sophisticated observational techniques in the pre-telescopic world, saw stellar twinkling as an indicator of earthly conditions and future events. They believed that the atmosphere, which they understood to be the breath of the earth, could reveal information about coming weather, political stability, and cosmic harmony through its effects on starlight. A night when stars twinkled peacefully was considered auspicious, while chaotic or unusually intense scintillation could portend storms, social upheaval, or the displeasure of the celestial bureaucracy that governed both heaven and earth. The Maya civilization, with their incredibly precise astronomical observations and complex calendar systems, incorporated stellar twinkling into their understanding of cosmic cycles. They noticed that certain stars twinkled more prominently at different times of the year, and they correctly associated this with seasonal changes in atmospheric conditions. However, they interpreted these patterns through their sophisticated mythology, seeing the varying intensity of stellar scintillation as evidence of the ongoing cosmic battle between the forces of order and chaos that drove the great wheel of time. In Norse mythology, the twinkling stars were sparks from the cosmic forge where the gods crafted the fates of mortals. Each flicker represented a moment when the divine smiths struck their hammers against the anvil of destiny, sending sparks of potential futures cascading across the night sky. Warriors who died bravely in battle were said to join this cosmic forge, their spirits adding to the twinkling display as they helped shape the destinies of those still living on Midgard below. Medieval European cultures, steeped in Christian symbolism, but still connected to older pagan traditions, saw stellar twinkling as the breath of angels. Each star was thought to be attended by a celestial being whose gentle breathing caused the rhythmic flickering of starlight. The more prominent a star's twinkling, the more powerful the angel that guarded it. This belief made the observation of stellar scintillation a form of prayer, a way of communicating with the angelic hosts through careful attention to their celestial breathing patterns. Islamic astronomers of the medieval period, who made crucial contributions to our understanding of optics and atmospheric phenomena, began to develop more scientific explanations for stellar twinkling, while still maintaining its poetic and spiritual significance. They understood that the breath of the heavens, their poetic term for atmospheric effects, was responsible for the dancing of starlight, but they saw this as evidence of divine craftsmanship rather than mere physical causation. The precise mathematical relationships they discovered in stellar positions and movements were understood as expressions of divine geometry, with atmospheric twinkling adding a layer of divine artistry to the cosmic order. Indigenous cultures of the Americas developed rich traditions around stellar observation that incorporated both practical navigation knowledge and deep spiritual understanding. Many tribes saw the twinkling of stars as a form of celestial communication, with different patterns of scintillation carrying messages about hunting conditions, weather patterns, and spiritual guidance. The intensity of twinkling on particular nights was often used to determine the timing of ceremonies, migrations, and other important community activities. Hindu astronomical traditions, with their sophisticated understanding of cosmic cycles and mathematical precision, interpreted stellar twinkling through the concept of Maya, the divine illusion that veils ultimate reality from ordinary perception. The flickering of stars was understood as a reminder that all apparent phenomena, including the stars themselves, are temporary manifestations of an underlying eternal truth that remains constant despite the dancing appearances that reach our senses. What's remarkable about these diverse cultural interpretations is how they all recognized something profound in the phenomenon of stellar twinkling. Whether understood as divine breathing, ancestral communication, or cosmic emotion, the gentle dance of starlight has consistently inspired humans to see connection and meaning in the apparent randomness of atmospheric scintillation. These ancient observers were responding to the same visual phenomenon that we understand scientifically today. But their interpretations remind us that scientific knowledge doesn't diminish the wonder and beauty of natural phenomena. It simply adds another layer to our appreciation. The transition from mythological to scientific understanding of stellar twinkling wasn't a replacement of wonder with knowledge, but rather an expansion of human appreciation for the complexity and beauty of the natural world. When we understand that the twinkling we observe is caused by the same atmospheric processes that bring us weather and sustain life on Earth, we're connecting with a truth that our ancestors intuited. The stars and the Earth are intimately connected, part of a single, integrated system of cosmic relationships. These ancient stories and interpretations remind us that the night sky has always been humanity's first and most enduring source of wonder, inspiration, and spiritual connection. As you rest beneath these same twinkling stars that inspired countless generations before you, you're participating in one of the oldest and most universal human experiences. The quiet contemplation of celestial beauty and the gentle peace that comes from recognizing our place in the vast, mysterious, and eternally creative cosmos that surrounds and sustains us. The twinkling stars above you tonight carry within their gentle dance the accumulated wonder of all human history. Each flicker connecting you not only to distant suns and atmospheric currents, but to the endless chain of conscious beings who have looked up at this same display and found in it reason for awe, gratitude, and the deep peace that comes from recognizing beauty in the natural world. Travelers of light and time. As you gaze upward at the twinkling stars in this quiet moment, you are witnessing the end of countless epic journeys. Voyages that began in the nuclear hearts of distant suns and traveled across unimaginable expanses of space and time to reach your eyes. Each photon of starlight that dances through our atmosphere carries with it a story of cosmic distances, stellar evolution, and the fundamental nature of light itself. These tiny particles of energy are among the most well-traveled entities in the universe, and their final atmospheric dance before reaching your retina represents just the last few dozen miles of journeys that may have lasted decades, centuries, or even millennia. Consider the remarkable nature of a single photon, born in the core of a distant star. In the unimaginably hot and dense center of a stellar furnace, where temperatures reach tens of millions of degrees and pressures exceed anything we can create on Earth. Hydrogen nuclei fuse together to form helium in the process that powers all stars. This nuclear fusion releases tremendous amounts of energy in the form of gamma rays, photons with incredibly high energy that begin their journey toward the star's surface and eventually toward us. But the path from a star's core to its surface is not a simple, straight line. The photon born in nuclear fusion must navigate through hundreds of thousands of miles of dense stellar material, bouncing randomly from atom to atom in what physicists call a random walk. Each interaction changes the photon's direction and often its energy, gradually transforming the high-energy gamma ray into lower-energy photons. This process can take thousands or even hundreds of thousands of years as the photon slowly diffuses outward through the star's interior, like a pinball bouncing through an impossibly complex maze. When the photon finally reaches the star's surface and escapes into space, it begins the next phase of its journey, the relatively straightforward trip across interstellar space to Earth. Here, traveling at the speed of light through the near-perfect vacuum between the stars, the photon maintains its straight-line trajectory for distances that boggle the human mind. If the star is like our nearest stellar neighbor, Proxima Centauri, the journey takes just over 4 years. If it's a more distant star, visible to the naked eye, the journey might take decades, centuries, or even thousands of years. During this interstellar voyage, the photon travels through what we think of as empty space, but which is actually filled with the faint traces of cosmic history. It passes through clouds of interstellar dust, the remains of ancient stellar explosions, and the raw material for future star formation. It encounters magnetic fields that thread through the galaxy, the gravitational influences of countless stars and planets, and the expanding space itself as the universe continues its cosmic growth. Yet through all of this, the photon maintains its course with unwavering determination, carrying its message of light across the vast distances that separate star from star. The photon you're seeing right now began its journey when the light left its parent star, which means you're literally seeing into the past with every glance at the night sky. The light from Sirius, the brightest star in our night sky, left that distant sun about 8.5 years ago. The light from the stars in the constellation Orion left those stellar furnaces anywhere from 240 to 2,000 years ago. When you look at the stars, you're not seeing the universe as it is now, but as it was when their light began its journey to Earth. You're looking backward through time itself. This temporal aspect of starlight adds profound depth to the simple act of stargazing. The photon dancing through our atmosphere and twinkling in your eye might have begun its journey when medieval cathedrals were being built, when ancient civilizations were at their peak, or when entirely different cultures inhabited the Earth. Each star carries light messages from different moments in history, creating a night sky that is actually a patchwork of different time periods, all visible simultaneously.
The journey becomes even more remarkable when we consider that some of the stars we see may no longer exist. A massive star that ended its life in a supernova explosion hundreds of years ago might still appear to twinkle in our sky if its light hasn't yet had time to complete its long journey to Earth. In a very real sense, the night sky is a cosmic museum preserving images of stellar phenomena that may have ended long before human civilization began. When the photon finally approaches Earth after its eons-long journey, it encounters our planet's atmosphere, the same ocean of air that we've been exploring as the cause of stellar twinkling. After traveling for years, decades or centuries through the vacuum of space, the photon suddenly finds itself in a medium that can bend, scatter, and redirect its path. The final dozen miles of the photon's journey through our atmosphere to your eye represent a dramatic change from the straight-line travel it has maintained since leaving its parent star. The atmosphere affects these cosmic travelers in ways that depend partly on their energy and wavelength. Blue photons, carrying more energy than red ones, are scattered more readily by air molecules. This is why our sky appears blue during the day, and why the sun looks reddish at sunset when its light must travel through more atmosphere. This same wavelength-dependent scattering contributes to the color variations we sometimes see in twinkling stars, as atmospheric turbulence temporarily separates the star's white light into its component colors. What's truly awe-inspiring is the precision with which these photons maintain their information during their cosmic journeys. The light reaching your eyes carries detailed information about the star that created it, its temperature, chemical composition, motion through space, and stage of stellar evolution. Astronomers can decode these messages, reading the spectrum of starlight like a cosmic biography that tells the story of stellar birth, life, and eventual death. The twinkling photon dancing through our atmosphere is not just light, but information, a cosmic data packet that has traveled across space and time to deliver news from distant suns.
The fact that we can see stars at all represents a remarkable cosmic coincidence. The universe is vast beyond human comprehension, and the probability that photons, emitted randomly in all directions from a distant star, would happen to encounter the tiny target of Earth seems vanishingly small. Yet here we are, catching these cosmic messengers in our eyes and telescopes, intercepting a tiny fraction of the stellar light that streams constantly through space in all directions. Modern physics tells us that photons experience no passage of time during their journey. From the photon's perspective, if such a thing can be imagined, it leaves the star and immediately arrives at your eye, regardless of whether the journey takes nanoseconds or millennia. This strange property of light-speed travel adds another layer of mystery to the cosmic journey. The photon that spent thousands of years diffusing through the star's interior and then centuries crossing interstellar space experiences its entire existence as a single, timeless moment. As you rest beneath this display of cosmic travelers, consider that your eyes are some of the most sophisticated photon detectors in the known universe. Each rod and cone cell in your retina can respond to individual photons, making your vision sensitive enough to detect light that has traveled across vast distances of space and time. You are, in a very literal sense, a cosmic archaeologist, using your eyes to collect and interpret light messages from different eras of stellar history. The gentle twinkling that draws your attention is thus revealed as the final chapter in epic stories of cosmic journey and transformation. Each flicker represents not just atmospheric refraction, but the culmination of processes that began in stellar cores, continued across the emptiness of space, and concluded in the complex dance of light through our planet's breathing atmosphere. In that twinkle, the nuclear physics of distant stars meets the fluid dynamics of Earth's atmosphere, creating a moment of beauty that connects the largest and smallest scales of physical reality in a display of natural artistry that has inspired wonder in conscious beings for as long as eyes have looked upward at the night sky.